Welcome to the Deep Dive, the show that cuts through the noise and extracts the most compelling insights from the latest research, custom tailored for you. We often take wireless communication for granted, don't we? Your home Wi-Fi, the 5G on your phone, LTE on your tablet, it all feels so seamless. Data just flows, instantly connecting you to information, entertainment, and other people across vast distances. But beneath that effortless, invisible flow lies an incredibly complex, often chaotic world. Data packets spanning interference, echoes, and constant dynamic changes in signal quality.
It's truly a marvel that it works at all, and at the absolute heart of making that miracle happen, silently orchestrating the flow is a crucial, often unsung hero. Automatic modulation classes.
Today we're diving deep into a fascinating breakthrough in this critical field. The Modified Resonant Dilated Convolutional Neural Network, or MRDCNN. This isn't just another incremental improvement. We're going to unpack how this specific deep learning model achieves superior accuracy and remarkable efficiency, especially for a technique called Orthogonal Frequency Division Multiplexing, or OFDM, which is, well, at the very core of your daily wireless experience. Our mission is to take what might seem like incredibly dense, abstract information
And transform it into surprising, actionable insights for you, revealing how these unseen algorithms are shaping our digital world. Okay, let's peel back the layers.
Yeah, what's truly remarkable here is just how foundational automatic modulation classification is to everything we do wirelessly. It's far more than a technical curiosity, it's an indispensable component for both securing sensitive communications in military or emergency services and for optimizing the raw efficiency of our everyday commercial networks. Without sophisticated AMC, our wireless world would be far less reliable, significantly slower, and much less secure. It really is the silent orchestrator, you know.
Ensuring that data packets arrive in a coherent, understandable form, adapting on the fly even when the channel conditions are fluctuating wildly, this is a foundational piece of the puzzle that
surprisingly intuitive, and it's critical to grasp.
Indeed. OFDM is an absolute powerhouse of a digital transmission technique. You might not recognize its name, but you interact with its results literally constantly. It's the primary backbone of your Wi-Fi router, it's central to how LTE networks operate, and it forms a fundamental core part of the incredibly fast 5G standard. So when your Netflix stream isn't buffering or your video call remains crystal clear even as you walk around your house, you can often thank the ingenious design of OFDM. It's what makes high-speed, reliable
wireless connectivity a reality in crowded environments.
But why is it so clever? What specific fundamental problem in wireless communication does it so effectively solve?
The main challenge OFDM masterfully tackles is something called intersymbol interference, or ISI. This is a familiar foe in wireless communication. Imagine trying to send a stream of digital data bits, like a rapid-fire sequence of individual sounds, very, very quickly over a wireless channel. That channel isn't a perfect, clear pipe. It's often a complex environment full of obstacles, walls, buildings, even people causing reflections, echoes, and multipath propagation. If you transmit symbols too
Rapidly, the echoes or lingering effects from one symbol can bleed into the next one, smearing them together. This smearing makes it incredibly difficult for the receiver to precisely tell where one symbol ends and
quite ingenious, actually. Instead of attempting to send one very fast, high-rate stream of data over a single wide-frequency channel, which would be highly susceptible to ISI, OFDM takes that wide channel and intelligently splits it into numerous narrowband subchannels, often hundreds or even thousands of them. Think of it less like a single, chaotic, high-speed highway lane and more like a massive superhighway with many, many dedicated slower lanes. OFDM then sends data in parallel over these individual lower-rate subcarriers.
by By doing this, it dramatically lengthens the duration of each individual symbol on its respective subcarrier. Because each symbol lasts much longer relative to the channel's echo time, those
This brilliant parallel processing maintains high data rates while profoundly countering ISI, leading to much more robust, reliable, and spectrally efficient communication, which is precisely why it's so ubiquitous.
That's a powerful analogy. It's akin to having many dedicated floor delivery trucks traveling on separate lanes, each carrying a small parcel of data, rather than one giant high-speed truck trying to navigate a single, congested, obstacle-ridden road. This distributed approach dramatically reduces the chance of data collisions or signal echoes interfering with each other, ensuring robust delivery even in challenging environments. But even with OFDM's ingenious solution, there's still a crucial overarching problem. How does the receiver know what language that
incoming signal is speaking? What specific encoding method was used? This is precisely where automatic modulation classification, or AMC, becomes indispensable. What's the real-world challenge it fundamentally addresses?
The challenge is absolutely fundamental to any wireless communication system. When a receiver picks up an incoming signal, it doesn't automatically know how that signal is packaged by the transmitter. Was it modulated using QPSK or APSK, or perhaps a more complex quadrature amplitude modulation like 64 QAM, or some other scheme entirely? If the receiver doesn't have a precise understanding of the modulation scheme used, it simply cannot correctly decode the information embedded within the signal. It's like receiving a coded message.
without the key, you have the data, but it's meaningless until you apply the right decryption algorithm. This is where AMC steps in. It autonomously identifies the specific modulation technique used in real time.
You're absolutely right. In military and intelligence scenarios, data security, stealth, and rapid analysis are paramount. Adversaries frequently transmit information using a variety of complex, often encrypted, or quickly changing modulation techniques to prevent interception and decoding by opponents. AMC is the critical, often first step for intelligence gathering and electronic warfare. By accurately and rapidly identifying the modulation type, it provides the key necessary for the correct decoding and analysis of the transmitted data.
This capability can ensure effective, covert communication for one side while providing a vital advantage in understanding an opponent's transmissions and maintaining robust data security.
Well, in civilian applications, AMC plays a massive, though invisible role in something called link adaptation. Picture your smartphone attempting to maintain a high-quality video call while you're on a train, zipping through urban canyons, or even just moving between rooms in your house. The channel conditions, the quality, and reliability of the wireless link are constantly and dynamically changing. If the signal is strong and clear, the transmitter can use a highly efficient, complex modulation scheme, like 256 QAM, to send a huge amount of data per second.
But if the signal weakens due to interference, distance, or obstacles, that complex scheme might start failing, leading to dropped packets or a garbled connection. Link
This real-time detection and classification by AMC allows for incredibly efficient use of the available spectrum, constantly optimizing the data transmission rate to match the current dynamic conditions. It ensures your video call remains stable, your streaming doesn't buffer, and your overall wireless experience is as smooth and reliable as possible, all while conserving precious bandwidth for everyone.
So just to make sure we're fully on the same page for our listeners, when we talk about modulation schemes, we're ultimately talking about the sophisticated ways in which digital information, those ones and zeros, are mapped onto
involve changing a single property, phase shift keying, or PSK, where information is conveyed by shifting the phase of the carrier wave, amplitude shift keying, or ASK, where the amplitude is varied, and frequency shift keying, or FSK, where the frequency changes to represent bits. These are foundational. But then you graduate to more complex digital modulations, often combining these principles.
Quadrature amplitude modulation, or QAM, is a prime example. It simultaneously combines changes in both amplitude and phase to pack significantly more data into each symbol. We have 60...
distinct fingerprints apart, even when they're mixed, distorted by noise, or changing dynamically. It's a truly formidable pattern recognition challenge.
It sounds like a perpetually evolving challenge, especially with the explosion of wireless devices and the demand for higher bandwidth. Given this growing demand and the critical significance of AMC in modern wireless communication, what's been the trajectory of research in this field? And where does deep learning, the core of today's deep dive, truly fit into this picture? This sounds like where it gets really interesting.
Right. Research in automatic modulation classification has indeed intensified dramatically over the past 2 decades. Historically, many AMC techniques relied on expert knowledge and meticulously handcrafted features. Engineers would spend countless hours designing complex algorithms to look for very specific statistical properties, spectral characteristics, or signal patterns that they believed were unique to a particular modulation scheme. These approaches were often rooted in classical signal processing theories like cyclostationary analysis
or higher order cumulants. They could be quite effective in controlled environments. However, with the increasing complexity and dynamic nature of modern communication systems, new modulators
absolute game changer, fundamentally shifting the paradigm for AMC. Their inherent strength lies in their ability to automatically learn and extract complex hierarchical features directly from raw signal data, instead of us, the human engineers, having to meticulously tell the algorithm what specific features to look for, what statistical properties, what spectral lines the deep learning model, particularly convolutional neural networks or CNN, discovers these features on its own. It's like handing a raw audio recording to an AI and having it figure out the language, the speaker's accent, and even their emotional state without ever being
explicitly taught those concepts. This self-learning capability significantly enhances performance, especially in highly noisy, dynamic, or previously unseen real-world conditions.
It's not just about applying deep learning, it's about a fundamental shift from human-engineered feature extraction to machine-driven discovery of patterns. Given that, we must have seen a lot of different deep learning models applied to this problem over recent years. What were some of the key prior attempts that set the stage for MRDCNN?
Yes, the field has been incredibly active and innovative. We've seen robust AMC approaches leveraging various convolutional neural networks, adapting architectures originally designed for image recognition to the unique challenges of signal processing. For instance, there's been extensive work on end-to-end CNN-based AMC models that automatically extract features from long sequences of raw IQ samples, and some even attempt to concurrently estimate the signal-to-noise ratio. Other efforts have focused on maintaining low complexity for real-time deployment, like
models using sparsely connected CNNs or highly optimized shallow networks. We've seen explorations of more established but adapted architectures like Visual Geometry Group or VGG.
OFDM signals specifically, one of the direct benchmark studies introduced something called the triple-skip residual neural network, or TRNN, which achieved about 91% overall accuracy for the same data set we'll be discussing. The common challenge, however, as the paper we're discussing highlights, is that many of these prior methods, while innovative, often presented a trade-off. They either performed commendably only at higher signal-to-noise ratios, meaning in very clean signal conditions, which are rare in the real world, or they were simply too computationally complex and
resource-intensive for practical, real-time deployment on typical hardware, especially on edge devices or in high-throughput systems. This inherent tension between accuracy and efficiency sets the perfect...
Which brings us directly to our star player today, the Modified Resonant Dilated Convolutional Neural Network, or MRD-CNN. This new model specifically aims to break that accuracy-complexity trade-off. So let's get right into it. What are the core contributions that make it stand out and position it as a significant leap forward in this domain?
Okay, the paper clearly outlines 3 key contributions, each building on the last. First and foremost, they propose a novel, deep learning-based algorithm, the MRD-CNN itself. This model ingeniously combines 2 powerful concepts, dilated convolution, which we'll definitely dive into, with a specially designed modified residual block for the task of automatic modulation classification. This architectural innovation is the foundation. Second, and critically, the MRD-CNN model demonstrates
superior classification accuracy. It consistently outperforms existing state-of-the-art models across a wide range of challenging conditions. This isn't just a marginal gain, we're talking about significant improvements
It truly is a double win. Better performance and less demanding to run, making it far more deployable in a variety of environments, from the data center to the smallest IoT device.
That's a powerful and compelling combination. Higher accuracy with lower complexity. Let's demystify one of those core components you just mentioned that's so central to this efficiency. Dilated convolution. How exactly does it work, and what's the underlying magic behind its ability to deliver so much with less?
Right, dilated convolution is a fascinating and incredibly clever variation of the standard convolutional operation, which, as we know, is fundamental to how CNNs process sequential data like raw signal samples.
In a normal convolution, you have a small filter, or a kernel, that slides across your input data, looking at a continuous adjacent block of points to detect patterns. If your filter is, say, 3...
looking at every single point. How does that help? Doesn't it miss information?
That's a great question, and it speaks to the magic. Think of it like this. Instead of looking through a solid small window to see the world, you're looking through that same size window, but it now has a mesh screen. The mesh has holes, but by strategically placing those holes, it still allows you to perceive a broader area of the scene, gaining a wider context without actually needing to physically make the window larger or add more glass. With the standard convolution, your filter might only see 3 adjacent points, giving it a very narrow local perspective.
With dilation, that same 3-point filter can now effectively see points that are much further apart across a wider span at the input, because it strategically skips over some points in between.
Context, the same computational cost. For signal processing, being able to see a broader horizon of the signal understanding longer range dependencies and more complex spread out patterns is vital for distinguishing the subtle yet defining differences between various modulation schemes, especially in noisy conditions.
So it's like wearing glasses with a really wide peripheral vision, but you're only seeing through specific optimally chosen points on the lens, rather than the entire surface. That gives it a much broader, more global understanding of the signal's characteristics without adding unnecessary computational burden. How is this given control? Is there a mathematical intuition behind it?
You've got the perfect analogy there. It's controlled by what's called the dilation factor, denoted as D. When D equals 1, it's just a standard convolution, meaning no gaps at all. But when D is 2, for example, the filter skips every other input element. The effective kernel size, let's call it K prime. K, for a given original kernel size K, changes according to the formula, K 1D plus 1. So a small 1/3 kernel with a dilation factor of 2 effectively behaves like a 1/5 kernel, but it only uses the original 3 parameters.
This allows it to cover a wider span of the input signal, capturing those extended patterns without adding more weight to the network, which directly translates to faster processing and less memory usage. This
residual network is, and then highlight how this MRV is unique or specifically tailored for this application.
Certainly, residual networks, or ResNets, were a true watershed moment in deep learning, primarily for solving a critical problem known as the vanishing gradient problem. In very deep neural networks, as you stack more and more layers, the gradients, which are the vital signals used to update the network's weights during the training process, can become incredibly small, effectively vanishing as they propagate backwards through the layers. This makes it excruciatingly difficult for the deeper layers to learn anything meaningful, halting the training process.
ResNets elegantly address this by introducing skip connections, also known as residual connections. Instead of a layer trying to learn the entire complex transformation from its
This innovation enabled researchers to build significantly deeper networks without encountering training issues, leading to much better performance across a wide range of tasks.
So the MRV in MRD-CNN is a clever variation on that core idea, tailored for signals.
Precisely. The modified residual block in MRD-CNN takes this proven concept and refines it specifically for the nuances of wireless signal classification. Its unique design employs a vertical concatenation of 2 distinct processing paths, both operating in parallel on the input signal. The first is what we call the main path. This path utilizes a convolutional layer with a specific 1/8 filter size, designed to capture
patterns across a short temporal or frequency span of the signal. The second is the skip path, which employs a much smaller but equally important convolutional layer with a 1/1 filter. This one
these 2 parallel branches are then vertically concatenated, effectively merging the insights from both.
And what's the specific purpose of this dual path vertical concatenation design within the MRB? How does it contribute to the overall model strength?
This design is quite thoughtful and contributes significantly to MRD-CNN's robustness. Firstly, the use of 2 parallel paths allows the network to learn and extract features at different scales or with different levels of granularity concurrently. The wider 1/8 filter in the main path can capture broader, more extended patterns across the signal, while the 1/1 filter in the skip path, despite its apparent simplicity, is excellent at processing information across different feature channels at a single point, refining the learned representations.
The vertical concatenation then efficiently combines these diverse multi-scale features, enriching the overall representation the network builds. Secondly, and just like in standard ResNets, this modified
inclusion of ReLU, rectified linear unit activation, functions in both paths further aids in learning highly nonlinear features, which is absolutely essential for distinguishing the subtle and complex nuances between various digital modulation schemes. Finally, following this intelligent concatenation, an average pooling layer with a stride of 1 is used. This pooling step helps to smooth out the features and reduce sensitivity to small spatial shifts in the input, making the learned representations more robust and generalize better to new, unseen
signals. It's a very elegant combination of techniques.
So that's the modified residual block. It's clear how that particular piece is engineered for signal processing. How do all these sophisticated pieces, the initial convolutional layers, the MOBs, and the final classification layers, fit together into the complete MRD-CNN model architecture? Give us the overall flow.
Okay, if you envision the overall flow, the model begins with the raw signal input. represents the in-phase and quadrature components of the complex signal, and 1024 is the number of samples in that signal segment. This raw input first passes through 4 dedicated convolutional layers. All of these initial layers are strategically designed to use a dilation factor of 2. These layers are crucial for automatically extracting those fundamental low-level features, things like phase changes,
amplitude shifts, and frequency variations directly from the raw time domain signal. They are the initial eyes of the network. After these initial feature extraction layers, the refined signal features are then fed
They leverage the unique dual-path structure, those skip connections, and the continued use of dilated convolutions to understand more intricate signal patterns, while simultaneously preventing the degradation in performance that can plague very deep networks. They are the analytical brain of the system. Finally, the high-level processed features that emerge from these modified residual blocks are fed into 3 standard dense layers. These are essentially your fully connected neural network layers, typical for classification. The very last
dense layer has 6 output nodes, corresponding precisely to the 6 different modulation schemes the model is designed to classify. This final layer uses a softmax activation function.
It's a sophisticated design choice based on the concept of feature hierarchy. Early layers need many filters to detect a wide variety of basic patterns, simple edges, various oscillation types. As you go deeper into the network, it combines these basic patterns into increasingly abstract and compact features. Think of it like a funnel. You start wide to capture everything, then narrow down to the most essential high-level characteristics. This significantly reduces the total number of trainable parameters in the network, leading to a much leaner and faster model
without sacrificing the ability to learn critical distinctions.
Right. If we connect this to the bigger picture, this clever architecture combining dilated convolutions for wider receptive fields with those modified residual blocks for deep learning and parameter efficiency is truly about optimizing how the network learns from signal patterns. It's about building a highly efficient yet powerful feature extractor for the complex, often subtle, nuances within wireless signals. But this raises an even more important question. How do they put this complex model to the ultimate test? How do they rigorously prove its
superiority and translate all this theoretical elegance into tangible, real-world performance metrics?
That's the million-dollar question, isn't it? Because in the realm of deep learning and machine learning, a brilliant architectural design is only as good as its demonstrated performance in rigorous real-world conditions. So let's talk about how this MRD-CNN was put to the test and the crucial role of the data set it was trained on. The foundation of any robust deep learning model, especially one designed for real-world application, is a high-quality, diverse, and representative data set. For this research, the team made a very smart choice.
They used an existing, publicly available OFDM dataset. This is important for 2 key reasons. First, it ensures reproducibility. Other researchers can access and verify their findings.
key characteristics that made it suitable for this kind of rigorous testing.
The dataset was generated using Genius Radio software, which is a powerful open-source toolkit widely used in software-defined radio applications and signal processing research. This approach allows for meticulous control over signal parameters and the simulation of various channel conditions, adding a crucial layer of real-world relevance. It allows researchers to mimic the complexities of actual wireless environments in a controlled, repeatable manner. The dataset itself is remarkably diverse, specifically designed to challenge a classification model. It includes
6 distinct OFDM modulation schemes. What's particularly interesting and adds to the realism is that the header and the payload of the OFDM signals could be modulated separately.
Absolutely. They highlighted several specific parameters for the simulated OFDM signals that are relevant to real-world systems. For instance, a 16-length cyclic prefix, or CP, was used. For those familiar with OFDM, you know the CP is an intentional redundancy added to each symbol to help combat inter-symbol interference caused by multipath echoes. A longer CP can mitigate more severe echoes, but reduces spectral efficiency, so 16 is a realistic choice. They also use 64 subcarriers, which dictate the number of parallel data streams,
And each OFDM frame was set to 186 bytes. These parameters reflect typical configurations in digital communication systems. Crucially, they rigorously tested the model.
This comprehensive testing across such a broad and challenging SNR spectrum makes the evaluation incredibly robust and directly demonstrates the model's performance in environments ranging from extremely poor to near perfect.
And what was the sheer scale of this data? We're talking about training a deep learning model here, so I imagine it needed a tremendous volume of information to learn from.
You're absolutely right. The volume of data was substantial, which is necessary for a deep learning model to generalize effectively. For each of the 6 signal types, under each of the 16 distinct SNR levels, they generated 4096 individual data pieces. Each of these pieces, in turn, contained 1,024 samples. When you multiply that out with 6 different modulation schemes, across 16 SNR levels, each with 4,096 data pieces, you arrive at a staggering total of 393,216 distinct data points.
That's a massive amount of information for the model to learn the intricate patterns and subtle distinctions between modulation schemes. Finally, before feeding this raw data into the neural network, it
Without this representation, the model wouldn't have the complete picture of the signal's oscillation characteristics.
That's a truly vast and meticulously prepared data set. So they have the data, they have the ingenious MRD CNN architecture. How do they go about the actual training process for this sophisticated model? What were the practical setup and parameters they used to optimize its learning?
Well, the training process follows standard, well-established machine learning practices to ensure reliable and generalizable results. The expansive data set was split into 2 main portions. 70% of the data was specifically allocated for training the model. This is where the network adjusts its internal parameters, learns from the examples, and refines its ability to classify. The remaining 30% was strictly reserved for testing its performance on unseen data. This is a critical step to prevent overfitting, which is what a model essentially memorizes the training
data, but then performs poorly on any new, real-world information it hasn't encountered before. As for the training parameters, they trained the MRD CNN for 100 epochs.
The Atom Optimizer, which is a popular and highly efficient algorithm for adjusting the network's parameters during training, known for its adaptive learning rate capabilities, set here at 0.01. These are all common, robustly tuned parameters for training deep learning models effectively.
And I imagine crunching through hundreds of thousands of data points with such a complex neural network, over 100 epochs, requires some serious computational horsepower.
It certainly does. The training and subsequent extensive evaluation were performed on high-performance computing hardware. An NVIDIA RTX 6000 GPU equipped with a substantial 24 gigabytes of dedicated RAM. This kind of powerful graphics processing unit is absolutely essential for accelerating the complex mathematical operations involved in deep
learning, specifically the matrix multiplications and convolutions, allowing the researchers to complete the training and testing within a reasonable time frame, rather than weeks or months on a standard.
numbers are frankly truly impressive and demonstrate a clear leap forward. For the overall SNR range spanning from that very noisy negative 10 dB all the way to the pristine 20 dB, the MRD-CNN achieved an average classification accuracy of 93.01%. That's an excellent overall performance across such a wide and challenging spectrum of conditions. But here's where it gets particularly remarkable and directly addresses the limitations of previous models. At 0 dB SNR, which is effectively a signal that's as strong as the background noise,
a highly challenging scenario for any receiver. The model still achieved a stunning 98% accuracy. Think about that for a moment. It's almost perfectly identifying signals even when...
That's astonishing. Does that mean that above 4 dB is effectively foolproof? Are there any theoretical limits to that perfection, or edge cases where even at high SNR, it might still struggle perhaps with highly similar modulation types? And what about the nuances how did it perform for individual modulation schemes, especially in those trickier low-noise conditions?
While 100% accuracy at higher SNRs is phenomenal, it speaks to the model's ability to extract definitive patterns when those patterns are clearly discernible. In practical terms, it means the system virtually never misidentifies a signal in good conditions. Theoretical limits often come into play at the very boundaries of signal physics or in scenarios with extreme, very specific interference. But for the given data set and noise models, it's effectively perfect. To answer your question about nuances, that's precisely where the confusion matrices come in.
These matrices are invaluable visual tools that precisely show how often each modulation scheme was correctly classified versus how often it was misclassified as something else. The confusion may...
and 91% overall was observed for QPSK, BPSK. This particular combination was sometimes misclassified as BPSK, BPSK about 6% of the time. This type of specific misclassification isn't entirely surprising to signal processing experts, as QPSK and BPSK can share some constellation points or symmetries that make them subtly similar in certain respects, especially when noise is present and distorting the signal. The highest accuracy in this full range was an impressive 95% for QPSK, APSK, showcasing its ability to clearly differentiate even complex mixed schemes.
The paper specifically highlights the model's performance at low SNRs, which is truly the acid test of robustness for any AMC system. For instance, at a challenging -4 dB SNR, which is
even in incredibly challenging high-noise conditions, where traditional methods might struggle significantly or fail entirely. It is truly remarkable to think about what this means for something like deep space communication or rescue operations in highly disrupted environments where you're essentially just trying to pick up a whisper in a scream of static.
That's fantastic robustness and precision. But the paper also discusses a crucial experiment that validates a core part of their design, the role of the dilation factor, that gap we talked about earlier. It sounds like that seemingly small architectural detail had an absolutely massive non-linear impact on the final result. Can you elaborate on that experiment and its profound findings?
You're absolutely right. This experiment is a direct validation of their architectural choices and really underscores the precise engineering required in designing these models. They conducted a targeted experiment to test the impact of different dilation factors on the model's overall accuracy, and the results, as shown in their comparative table, are incredibly telling and quite dramatic. When the dilation factor was set to 1, meaning there was no dilation at all, it was just a standard convolution where the filter looked at strictly adjacent points, the overall accuracy of the model was a respectable 85.20%.
Still good, but certainly not groundbreaking. This serves as an important baseline, showing what the network can achieve without the magic of dilation. Then, when they increase the dilation...
It truly leveraged that magic of dilated convolution to its fullest. The network could integrate more global information without becoming computationally heavier.
Okay, let's really unpack this. Why does that small change in the dilation factor have such a massive, almost binary impact? And what happens if you go too far, pushing the dilation factor even higher? Is there a point where too much gap becomes detrimental?
This is where it gets critically insightful. If you push the dilation factor to 3, meaning the filter skips 2 elements between each active point, the accuracy plummeted to a mere 16.70%. This catastrophic drop isn't just a slight decrease, it effectively renders the model useless. This dramatic failure occurs because with an exponential increase in the effective kernel size and the sparsity of active points, the filter essentially becomes too diffuse, too disconnected. It has so many gaps that it starts skipping over too much relevant,
fine-grained information and local coherence that are absolutely essential for accurate pattern recognition in signals. It's like trying to read a book where every third word is missing and then every third sentence.
It highlights the incredibly precise, almost artistic engineering required in designing these deep learning models. Small changes in hyperparameters can have profound and nonlinear impacts on performance. It's about finding that computational sweet spot.
So we've seen that the MRD-CNN performs exceptionally well on its own terms, achieving remarkable accuracy even in noisy conditions, and proving the brilliance of its dilated convolution component. But the ultimate test for any new model is how it stacks up against the competition. Specifically, you mentioned the TRNN model earlier, which is a direct benchmark for OFDM signals. How does the MRD-CNN truly shine when placed side by side with the best existing solutions?
This is indeed where MRD-CNN's capabilities truly differentiated. The TRNN model, prior to this research, was the only existing method specifically addressing modulation classification for OFDM signals using a similar deep learning approach, making it the most direct and relevant competitor. The paper then illustrates this comparison meticulously, evaluating performance across different sampling rates and SNRs. What's immediately evident is that the MRD-CNN consistently delivers superior results compared to TRNN across the board. This is particularly pronounced at higher
SNRs, where signals are clearer, and, crucially, at lower sampling rates, which we'll discuss as a major practical advantage. Let's look at some specifics. For a standard sampling rate of 1024 at a
accuracy, again outperforming TRNN by 2%. These are not marginal gains. They demonstrate a robust and consistent superiority.
And you highlighted its even better performance at lower sampling rates. Why is that incredibly important for real-world devices and applications? It sounds like it implies a broader impact.
This aspect is a huge win for practical, real-world applications, and is perhaps one of the most compelling insights. At a lower sampling rate, say SR512, MRD-CNN's lead becomes even more pronounced. It surpassed TRNN by 10% at -2 dB SNR and by 4% at 6 dB SNR. The difference becomes truly dramatic at an even lower sampling rate of SR256, where MRD-CNN outperforms TRNN by a massive 26.34% at -2 dB SNR and an impressive 15.07% at 6 dB SNR.
What this means is that MRD-CNN can achieve high classification accuracy even when it's fed significantly fewer samples of the incoming signal. Why is this so crucial? Because
effectively extracts superior features and maintains high performance even with a reduced amount of input data, which is a powerful testament to its intelligent and efficient design. It's doing more with less data, making it far more versatile for deployment. It's important to acknowledge that there was a minor exception to this dominance. TRNN was slightly better at very, very low SNRs like -10 dB, -8 dB, and -6 dB for the SR1 or 24. However, the overall pervasive trend clearly indicates MRD-CNN's superior performance across the
vast majority of practical and commonly encountered SNR values, and critically, across all lower sampling rates, which are so vital for deploying these systems on constrained hardware.
Beyond just TRNN, how did MRD-CNN fare against a broader range of other state-of-the-art deep learning models, commonly used for automatic modulation classification? Was it really better than its direct competitor, or is it setting a new benchmark across the wider field?
It's definitely setting a new benchmark. The researchers didn't just compare it to TRNN, they benchmarked MRD-CNN against several other well-known and established deep learning architectures commonly applied to AMC. These included a VGG-based neural network, a classic ResNet architecture, a multi-skip ResNet, MRNN, and a cost-efficient CNN architecture known as MCNet. These are all formidable competitors, each with their own strengths. When looking specifically at classification accuracy at 904 dB SNR, a challenging mid-range noise level
That represents a realistic operational environment, MRD-CNN clearly led the pack. It outperformed MCNet by a significant 5.5%, MRNN by 2%, and both the
This is all about performance, and MRD-CNN is clearly a standout. But you also mentioned complexity earlier, specifically that MRD-CNN is less complex. How do they quantify that, and how does it stack up against these other top-tier models? Because often, the intuitive expectation is that better performance comes with more complexity, not less. This is the aha moment, isn't it?
This is indeed the crucial aha moment, and it truly makes MRD-CNN a standout in the field. Complexity in deep learning models is most commonly measured by the number of trainable parameters. These are essentially all the weights and biases within the neural network that the model needs to learn and adjust during the training process. A higher number of parameters generally means a larger model, which typically translates to more memory usage, slower inference times during deployment, and greater computational demands for both training and operation. And here,
MRD-CNN truly excels in a way that often contradicts intuition. It has the lowest complexity among all the compared models, boasting only 132,000 trainable parameters.
MRD-CNN still manages to be leaner, with 7% fewer parameters. This raises an important question, really. How does having fewer parameters, despite achieving higher accuracy, translate to tangible, real-world benefits for us and the devices we use every day?
That's the crux of it, isn't it? Because in the real world, it's not just about a percentage point of accuracy on a chart. It's about deployability, practicality, and efficiency. What does this reduced complexity mean for wireless system operating out in the field?
Exactly. Fewer parameters mean a significantly smaller model size, which directly translates into several crucial practical benefits across the entire ecosystem of wireless communication. First, for deployment. A smaller model is inherently easier and faster to deploy on resource-constrained devices. Whether it's a smartphone, a drone, an Internet of Things sensor that needs to run on minimal power, or an embedded system in a vehicle, a compact model requires less storage space on the device and consumes less RAM during operation.
This drastically expands the range of hardware it can run on. Second, energy efficiency. Running a smaller model requires substantially less computational power. This directly translates to lower
performance classification task much faster. This is absolutely vital for applications like link annexation in mobile networks, where decisions about modulation changes need to be made in milliseconds to maintain seamless communication, or for tactical military communication, where instantaneous identification of a signal could be mission critical. So MRD-CNN's ability to not only outperform these other state-of-the-art models, including TRNN, but to do so despite having fewer parameters, is a powerful testament to its incredibly efficient intelligent and smart design. It's doing more with less, which is precisely
The holy grail in cutting-edge, resource-constrained wireless technology.
That's a truly remarkable combination of superior performance and profoundly reduced complexity. It feels like a significant foundational step forward in how our wireless world operates. So, to bring it all together for our listeners, what are the core strengths of the MRD-CNN model and its most critical implications for the future of wireless communication?
The core strength of the MRD-CNN model is its unique ability to drastically improve automatic modulation classification accuracy in orthogonal frequency division multiplexing, or OFDM, systems, while
Simultaneously keeping its computational complexity remarkably low. Those impressive accuracy figures, 93.01% overall, 98% at 0 dB SNR, and a
It matters because accurate and low latency signal classification, as achieved by models like MRD-CNN, directly and significantly enhances spectrum efficiency across all our wireless systems. Think about it. Currently, in many systems, devices often have to transmit some form of explicit signaling information to tell the receiver, this is what kind of signal I am, this is my modulation scheme. This uses up valuable bandwidth, the bandwidth that could otherwise be used for actual data transmission for your videos, your calls, your IoT device data.
by allowing the receiver to automatically, instantaneously, and accurately identify the modulation scheme without being explicitly told, models like MRD-CNN effectively eliminate the
The invisible language of wireless more transparent and immediately understandable for our devices without costly overhead.
So it's not just making existing systems better, but potentially paving the way for future innovations that are even more bandwidth hungry or latency sensitive systems we can barely even conceive of today. What are the next horizons for this kind of research according to the paper itself, and what should we be looking out for?
The researchers themselves point to exciting and vital future directions. They plan to expand their work by exploring other modulation schemes beyond the 6 included in this initial dataset, which will broaden
the model's versatility and applicability across an even wider range of communication systems. And critically, they aim to continuously push the boundaries by improving accuracy at even lower
And that brings us to a thought-provoking idea for you to consider as you go about your day, connected by those invisible waves. Think about how advancements in machine learning, by making these invisible signals transparent and immediately understandable, are not just optimizing our current wireless infrastructure, but fundamentally laying the groundwork for even more innovative, efficient, and robust communication systems we can barely imagine today. What other invisible systems around us, perhaps in complex biological processes,
Intricate financial algorithms, or even the nuanced patterns of human behavior could be similarly transformed by smart AI, making the complex simple and the hidden visible?